Okay, so first thing I want to talk about is the announcement about the exam, the cheat sheet for exam three. So obviously, as uh, those of you that have been going through the modules have noticed, some of you commented, which is great. There's a lot of equations in this coming exam. So yes, there is going to be a math heavy portion compared to the other exams for this one, which is why I'm allowing the cheat sheet, which is your standard 8.5 by 11 printer paper. You can use front and back of it. The only stipulation is it has to be handwritten. So I want you to, take your time to make your notes. You can put anything you want on the exam. You can put definitions, not on the exam, sorry, on the cheat sheet. You can put definitions. You can put the equations, which is something that I highly recommend. You can put example activities from cog books. You can put notes from the reading. Yeah, so anything is free game. I just ask that at the beginning of the exam, you show the front and back to the camera, just so it can, briefly, just give it, good 1,000, 1,000, turn it, do the same thing. That way we can just kind of, see briefly what's on there, if there's any, question or anything like that. Um, yeah, so is there any questions from the group about the exam three cheat sheet?
Thank you.
Yeah, no problem. Figured that might be good to clarify a little bit and also not having to memorize, the numerous equations in there. Because a good strategy might be to put the equation, but also to put like what the equation means, what is it measuring, as well as what are the variables, right? Because you've seen some of the activities probably where they're like, what tells us, that this is the population at age two, right? So know how to find something like that. And we'll go over that in a lot more detail with the activities from tonight. But just as a reminder, the exam opens on Tuesday and goes through Wednesday, so the 11th through the 12th. Like normal, it's through honor lock. Once you open it, you got to finish it. If you experience technical difficulties, do let me know. Like CC me on the emails, but most of the time those are going to be something you'll have to, talk to IT or cog books about, as they'll be able to help you on the IT side better than I will be able to, because that's who I'm gonna, turn to with a lot of the questions. But hopefully it'll run smoothly. This is we're getting a little more used to it now. So it'll be our third exam. Um, and tonight it's gonna be a little bit longer probably because we're gonna go over three sections, and I do want to go over some examples and some of the calculations with you. So is there any questions about the course in general or the exam before we get to the content of the first three modules?
I have a general question. I've been drinking the Kool-Aid without understanding it. On dn over dt, d is the derivative, and how how is that determined? The derivative. It's an
Uh,
ecological variable. Where do we get it?
it's a rate function, right? So it's going to tell us a derivative is a rate of anything. It could be water draining through a bathtub. That's a classic example in calculus. For us, a lot of the times it comes from the equation specifically. So like the logistic growth, you can get a derivative out of. But I will say, make a note too that because calculus is not a prerequisite for this class, you won't be asked to calculate any derivatives on the exam.
Thank you.
So cogbooks, as you'll see, will go a little bit deeper than I'm going to ask, and I'll try to clarify that as best as possible tonight, tell you which equations to really focus on for calculations and which ones to understand more conceptually of just what do they tell us kind of thing. I'm going to go ahead and share my screen then. Okay, we can all see my cogbooks, okay? Okay. So to start with, it starts pretty basic where we talk about the whole concept now is estimating population growth. And as you've seen, there are many ways to do that. Some decent ways and some better ways or more decent ways. They range, exponential growth is going to be the most simplistic way to do it. And I think it's important that we see some of the simple methods and some of the more complex methods because it shows us how ecology kind of started, what the limitations were, and how ecology grew a bit and makes, we can make more accurate predictions. So the exponential growth model is the most simplistic one. This is the basic model here. N of t equals n0 e to the power of RT. And if we just kind of break that down, N of t, we're just estimating population numbers at a specific time, right? That's what the t stands for. That could be, a month in the future, a week in the future, a year, 5 years in the future. So t is just a placeholder for whatever time interval we're looking to estimate for. N of 0 is going to be the n of the population number at time 0, so the current population. And if we want to estimate, 3 years into the future, it would be n of 3 equals n of 0 e to the r3, right? R is going to be our rate function, so the population's intrinsic growth rate, and T is going to be the amount of time over which the population grows. And they give us an example where they provide some data, right, where you have 100 mice, and their intrinsic growth rate is 0.4, and we're looking over a 5-year period. So the way they plug it in, it's n of 5, that's what we're predicting, equals n of 0, which is the 100, that's what we're starting with. E is a built-in function. So this is going to be important for the exam. You are going to have to be able to have a calculator of some sort that can use E or a log potentially. So make sure ahead of time that you have a calculator. And again, it can be a scientific calculator. It can be a calculator on your computer that'll be on the screen, but it can't be, a tablet or a cell phone that has Wi-Fi access. That's the restrictions again on the calculator. But then we raise it to the power of r times t, and that's 0.4, which we were given, and then 5, which we were given. Plug it in, do the math. In 5 years, the population should go from 100 mice to 739 mice, right? And then they show this is kind of the estimate of what an exponential function looks like. And this is using the exponential equation with some real data. So it's the same general pattern, but you can see it's a little more jagged. It's not as smooth. Yeah, so that takes care of, and then this here gets us to the derivative where we can estimate, what does it say? We can estimate the rate of growth at any point in time. So what it does is you take the log of both sides of the equation. So the log of this and the log of this side, that's why you have a rate function and it gets rid of the e because the log function brings that down. But again, we're not doing, calculus isn't a prerequisite, so we don't need to go over practice calculating this. Then just kind of go in a little bit more detail than necessary of how we get potential, calculate the rate at any one point. Okay. And then we have the geometric growth model, which is kind of similar, but what's different about it? If we look at it, the figure, this is exponential and this is geometric. They look pretty similar, but we have some dots on the geometric. What do those dots represent? It's comparing population growth at what?
Specific times.
Yeah, regular time intervals, exactly. So at time 0, time 1, time 2, where the exponential is theoretically continuous, like you can pull it over at, any point at any time, where the geometric is a little more plug and chug, you're going to get more specific time points that you put in. And the equation set up, where we have n of t equals n of 0 lambda to the t. So n of t, again, is just our estimate of our population at a specific time. N of 0 we already defined is our starting population. Lambda, that's going to be a value. I'll be honest, I don't know exactly where lambda came from. but there are papers that have the proofs where they actually go through and derive these equations that we can look into if we want. That's not going to be something we're held accountable. So again, this isn't supposed to be, a math class, so I'm not going to go into, researching the proofs and go through it together. Rather, just how we use the function is going to be more important for this class. And here they have the example. We have 100 quail, so that's our n of 0, right? Our growth rate, our lambda, is going to be 1.5. And then after 5 years, what is the population? So we have 100 times 1.5 raised to the fifth power. Calculate that out. It equals 759. So this is another population of quail that we show has grown over 5 years. What are some of the assumptions of both the geometric model and the exponential model? Assumptions are going to be important to understand and remember for the exam. Assumptions about the population and the members of the population, let's say.
There's no immigration or immer or extra immigration in
Yeah,
that.
exactly. That's one of them. There's no immigration, there's no emigration, right? It's not accounting for that. Um, what about something like resources in the environment?
Unlimited and exponential.
Yeah, and they're pretty much unlimited in geometric too, right? It assumes that there's no limitation because as we'll see with the logistic growth very quickly, there's something in that equation that accounts for limitations in the environment. What about the individuals? How does it treat the individuals, both of these equations? Say we're talking about a deer population. Does it assume they're all the same, or does it assume differences among individuals?
It assumes they're all the same.
Yeah, right. This assumes that all individuals have the same probability of surviving, and all individuals have the same probability of reproducing. So again, very basic. It's missing some key ecological points, but we can get some population, some rough estimates using these equations. And here, this is something that's interesting too, right? It talks about the values of R and the values of lambda. For lambda, if it's greater than 1, it's going to be, or if it's less than 1 here, it's going to be decreasing. If it's equal to 1, we have a stable population. If it's greater than 1, it's going to be increasing. And this is supposed to be lambda, but it got kind of cropped out of this image in cogbooks, unfortunately. And then same with R, right? If it's less than 0, we're going to have a decreasing population size. If it's equal to 0, it'll be stable. And if it's greater than 0, it'll be increasing. So these values are going to be important to recall how they relate to the growth of the population. Okay. And then it gets into doubling time. And what is that in a nutshell, briefly?
Basically just doubling in abundance, like number.
Yeah. So it has to do with doubling in abundance, absolutely. But here we have n of t, so it's time, right? So we're interested in kind of how long it would take a population to double in size or in numbers. And this just kind of walks us through another example using the equation of how we get to doubling time. In this particular population, based on the values that it gives us for lambda, it would take them, what it says, 246 days, so T2 time point 2 to double in population. Okay, and then it gets into density dependence. And the way Cockbooks describes that is it's just factors that affect population size in relation to the population density, right? And then there's two types of population or density dependence. There's positive density dependence and there's negative density dependence. And it goes into these individually, which is kind of nice to kind of break them down. So it starts with negative density dependence, which we know occurs when the rate of the population growth decreases as the population density increases. If we look at a figure here, we have population density increasing from left to right, and then we have progeny per adult fruit fly. So this is the amount of offspring that they're producing at this greenish line right here on the left. And as the population increases, each adult is producing less and less. So as the population is increasing, it's increasing at a slower rate, essentially. And it also has an interesting data point that it shows the adult lifespan. As the population increases, initially increases and then it decreases. Why do we see these decreases, do we think? Why is the population not reproducing as rapid as it grows? So we have more individuals reproducing less.
Because now there's limited resources that are being dispersed amongst a bigger
Exactly.
population.
Yep. So if we say this environment has a finite amount of resources, we're dividing that by more and more individuals. So each individual in that population, as it grows, gets less and less of that resource. So they're able to, we think back to our previous exam, the allocation principle of allocation. So resources, right? They can only allocate so much from the environment to an organism, and if they get less, they can only allocate, even less to their reproductive efforts. We get a similar pattern with these birds here. And their limited resource here was nesting site, right? So when there were a few birds in the beginning, so this is number of turns in the thousands, it initially increased pretty fast and then it kind of plateaued, right? Over time because there weren't open nesting sites. And actually part of the story is they moved from Bird Island to Ram Island and they, had initially really fast growth. It's not as clean, but it kind of says that it plateaued here. And then they even moved off of Ram Island to this Pennikes Island and had initial increase in growth. So just they ran out of the resource here was a nesting site, and they had to either the population plateaued or it could move to a different area. And then this was kind of like a density dependent study. So what we're looking at is they had three different treatments. They had one group where they planted 60 seeds per square meter, one group where they planted 1,440 seeds per square meter, and then this group over here, the highest density was 3,600 seeds per square meter. And then what they're measuring is prevent individual the flax plants. So this is a frequency distribution, and then plant dry mass. So the height of this each of these bars is just the percentage at one of these different dry masses. And we see at the low density, we have an average of maybe a little bit less than 1, right, for plant dry mass. And then at the medium density, that average gets shifted over. So they're smaller plants, right? There's less dry mass per plant. And we see this shift in this frequency distribution, again, because they're competing over limited resources and there's more of them. So we're getting smaller and smaller plants as the trade-off. They can't produce as many or produce as much mass to themselves. So their leaves are smaller, probably less seeds and less stems. And then we kind of see the same thing here. So this is horseweed plants per square meter in green. So as this is the density is going down for the green line as we go left to right, and then average plant dry mass in the orange. So as the density goes down, the plants have more mass. So this is the exact same pattern that we saw in the other plant species too. Again, that's just due to limited resources. Okay, and then we have a positive density dependence, which has another name. They call it the inverse density dependence or the Lee effect. because this occurs when the rate of population growth increases as the population density increases, right? So it's all positive versus being negative like the last one. Why would we see, or when would be a good scenario when we would see positive density dependence?
When a population density is low.
Yeah, and why would it be a positive growth when it's low? It's something we've already talked about.
Because there's more available resources.
Yeah, exactly, right? So when you have a few plants, one reason is they're not really competing over resources because they're plentiful to the number of plants right now. Another reason is possibly because these plants might need to pollinate with one another, so they initially might have slow growth because it's hard for insects to find that plant when there's only a few of them. But as there's more and more of them are common and more get pollinated, they can continue to grow as long as they have their adequate resources. And what is this figure showing us right here? We're seeing positive density dependence and negative density dependence in the same figure, right? So it's telling us that maybe these two aren't mutually exclusive. As we talked about, when there's small population sizes, we might see initially a positive density dependence where we have this rapid growth. And when the resources start to become limited, competition increases, we're going to get a switch to a negative density dependence. And eventually, if the population grows too much or gets too large, the growth rate's going to drop potentially to zero and maybe even go to negative. We might have a decline in the population if they can't, if they can't sustain themselves. This is just a real life example of with fish of showing how initially it increases and then when it eventually will switch to negative density dependence. Okay, and as we've alluded to, with lack of resources or limited resources, increased competition. This is a logistic growth curve. It includes another factor in the environment or in the equation that we haven't seen yet, and that's K, right? And what is K?
The carrying capacity.
Yeah, it's the carrying capacity for a given population. So it's going to kind of look like exponential growth initially because there's going to be rapid growth. And then when it reaches its, or nears its carrying capacity, it typically will tend to plateau and stay right along this, the line of its carrying capacity. And what is carrying capacity indicator? What is it? How do we define it?
It's basically the population size that can be supported by the environment.
Exactly, right? It's the maximum population size that can be supported. Can they ever go over carrying capacity, a population?
Yes,
Yes.
And what happens when we see that?
crashes.
Yeah, it usually doesn't last very long, right? We'll get into figures like that. It'll go past it, but then there's going to be a die-off, and usually the die-off will cause it to go below. And when you go below, you have more resources than you can go above, and that'll eventually will get into kind of that cyclical pattern that we'll see for populations.
Can I ask you why they didn't use C for carrying capacity? Is it used because C sometimes is competition?
That's a really good question. I have no idea why the person that derived this equation didn't use C, but it might be something that it was a common term in a different equation at the time. And we don't have to worry about derivatives or log transforming it. It's something interesting to know, but we're not going to get that advanced in math in this class. And then this is just kind of showing it in real life and how different levels of food can actually change the carrying capacity, right? Because resources in an environment might change. And one of those resources that limits carrying capacity is food. So they gave these paramecium low food supply and high food supply. You can see both populations initially grew. Not surprising, low food supply has a lower carrying capacity than high food supply in both species. So this is very basic but very clean depiction with real data of what a carrying capacity kind of looks like. What are some other things that could potentially change the carrying capacity besides population and food? What are some things maybe that could affect the environment from the environment that could affect the population?
Climate, disease.
Yep, climate's a great one,
That's-
and that could be broken down to, it could be temperature, so it could be really hot where there's maybe a drought. They don't have much water or food around because of the hot temperature, or it could be cold. You get late season snow or frost can really crash populations, so it could lower the carrying capacity of that environment. You said disease is another good example. We'll get into this in a little bit, but predators, they're definitely a factor when it comes to carrying capacity. You got a lot of predators eating a lot of prey. It's going to lower that carrying capacity. The predators die off potentially because of disease. It's going to raise that carrying capacity of that environment. Okay, so this is pretty basic. Activity field is kind of matching here. We're going to have the exponential growth versus the logistic growth, that unchecked growth versus the kind of with the carrying capacity, that S curve. And then it asks about competition. So with exponential growth, do we have any competition?
No.
No, right? So it assumes that there's no competition, unlimited resources. And then logistic does assume a little bit of a competition, but intraspecific. So that's within the species. So if we're talking about deer, it's just deer competing with deer is the competition, not necessarily deer competing with birds or competing with rabbits for food resources. Maximal growth rate, right? We're going to see just straight up R for here. And then they kind of change up the equation a little bit, but it's going to be this one here. Equilibrium size, there is no equilibrium with the exponential growth, right? Versus the equilibrium size is going to be carrying capacity here. And then the difference between the two different equations. You can check the clock books. Yeah, it agrees with us. Okay, and these activities are, I think, pretty good. They ask some pretty interesting questions. And obviously I click through them so you can see the answers, but nonetheless, let's talk about the why a little bit, because that's going to be important to understand for the exam. So it says, which model assumes that individual species compete for resources, right? And that's going to be the logistic growth equation. But why? What about the equation, or where is the assumption, maybe I should say, in the equation for competition? It's the variable that logistic has that exponential doesn't. It's the carrying capacity, right? That's how we know they're competing for resources, because they have a limitation on what their population level can be. There's a cap on it. All right. And we kind of talked about this one already. Which model assumes resources are unlimited? That's going to be the exponential as well as the geometric. Which model assumes that individuals in the population are identical? That's going to be both models, right? There's no difference in assumptions for reproduction or survival. So both, really all three, right? The exponential, the geometric, and the logistic. I don't know why they excluded the geometric in this, but it's part of this as well. So they all assume that the population are identical as far as reproductive potential and survival potential or probability. So which models assume individuals in the population differ? So that's just the opposite, right? The correct answer is neither model. And then which model describes a population that grows exponentially. I mean, that's going to be the exponential model, but I really don't like how they set this up because in the next question asks which model describes a population that never grows exponentially. But if you recall from the previous figure of the logistic growth, it says in comp books, initial growth is exponential like. So I would argue that it doesn't continuously grow exponentially, right? We see that inflection point where it goes to plateaus and the growth rate, tends to zero. But in the beginning, there could be an argument that it, in some instances, it could potentially start as exponential. Okay. And then these are good because you'll see kind of some exam questions that are similar to this, right? It presents you an equation, and then it might ask you something like, which term in the model describes the number of individuals, right? And then we just that's part of where we have to know, having our cheat sheet with our notes are going to be nice. If we put the models on there, kind of have a key for those models, these types of questions should be pretty simple. Right? So that's just going to be N, that represents the number of individuals. Which term in the model describes the per capita growth rate in population growth? That's going to contain something with an R. That's our growth rate. So this part of the equation here. Which term of the model describes the number of offspring born in the population? And this one is none that are provided, right? So we haven't gotten to that. That'll be in later modules where we'll get to that. But we got to know that the exponential model, the geometric growth model, and the logistic model don't tell us that. Okay, and then this activity is a calculation. So if it gives us N, R, and K, which model are we going to use?
Logistic.
Logistic.
Yep, we got K, so we know that that's going to be the logistic. And we plug it into the equation that we'll have on our cheat sheet and do simple math and use our calculator or by hand, however you want to do it. And we can calculate in that equation that it would be 22 here. Okay. Then this one was kind of an interesting thought exercise, I thought, where they use some of these models, they're using logistic growth to estimate human population growth. And what we have is we have two models on here. We have this dotted line, which is the predicted logistic growth based on the numbers that we have, right? So they plug it in, everything's aligning really, really well, really perfect, but then it deviates, right? It actually makes that prediction, the inflection point is going to be somewhere around here, versus the actual numbers show that the population is continuing to grow almost in an exponential way, but kind of you can see it's slowing down slightly, but it still hasn't had that real inflection point. What were some of the reasons that they gave that the US population continued to outpace what was predicted through the logistic growth model?
I remember it saying that it was when we kind of discovered or were able to resource from other countries that we were able to increase our resources, and that's why it wasn't initially in the time frame they created the model something that was considered.
Yeah, so the logistic growth model doesn't have certain assumptions built in, right? And what you said was one perfectly. We have a finite number of resources we can produce in the United States food resources that can feed our people, that can allow our people to grow, right? But we also have shipping and trade with other countries. So we can ship extra food to increase the amount of resources available in our country, in the US, which will then raise the carrying capacity of the United States. What was another factor that the logistic model failed to incorporate?
Immigration.
Yeah, it doesn't account for immigration or emigration, people coming to the United States or people leaving the United States. And there was more people that immigrated to the United States during this time period that left, so that added to the population as well. And then the third one was technological advances, right? This is from technology increasing from the late 1700s to the early 2000s, right? That's a lot of time and a lot of technology, right? So especially in like agriculture, there's a lot of technology that allowed the United States to increase its food production. So the amount of food that it had and created or produced increased, the amount of food it brought in increased. So this is why it kept raising the carrying capacity in real life compared to what the logistic growth model predicted. Okay, are there any other questions from module 3T9, this one that we went over? That covers what I wanted to go over for this module. Okay, if not, no worries. We can always send questions later through email if they come up. We'll continue on to the second one for this exam, module 3T10. So this one is about population cycles. In this first one, they talked about kind of a real life example about moose as prey and wolves as predators. And they've done some observations on this island in Michigan called Isle Royale. And it's actually pretty interesting because the moose and the deer, or the moose and the deer, the moose and the wolves are more or less locked on this island during the warm season. And when winter comes, the water freezes over and they can actually freeze to the island where the moose and wolves can immigrate and emigrate on and off the island. But the wolves, part of it were the predators and the moose are the prey. They don't have a figure with it, but the point is it's introducing the population cycles. When the wolves eat the moose, the predators have more resources that they can put towards reproduction, and their numbers tend to grow. And then the moose obviously are being eaten, so they're being removed from the population. They tend to decrease in population. But after a little while of that inverse relationship, with the moose going down, the wolves don't have as much resources, so their population goes down. But there's this lag effect behind because it takes time to convert food resources into offspring, and it takes time for offspring to potentially die or adults to die when the resources are depleted. So then the wolves start dying, and then because there's less predation pressure, that gives time for the moose population to rise. But when that moose population rises, the wolf population will rise behind it and knock it down, and that's where you get this oscillating lag effect where it's the predator-prey cycle on the population numbers. Okay. And this is just a very basic graph. Not surprising that populations cycle over time. We've kind of already talked about this, so we don't need to drone on it too much. But obviously, things that affect population cycles are going to be predators. Things that are going to affect population cycles are going to be diseases we mentioned. Could be parasites. It could be climate, so temperature, rain. If it's really dry and really warm, right, we're not going to have many plant life. So that's going to drop the herbivore populations down, which will then drop the predator populations down. So there's many things that can affect these population cycles. Humans are a big impact to affecting population cycles. With deer in particular, if there's a hunting season, right, the population tends to drop a little bit because you hunt when it's a non-breeding season in most instances. And then the hunting season stops. They go through the winter usually, and then in spring they give birth, and then the population increases quite a bit. So humans can kind of act as a de facto predator as well. In fact, they do it a lot in a controlled situation where if the deer population is getting very large in certain areas in the US, it leads to a lot of automobile crashes, a lot of crop damage. That's how they determine usually how many tags that they hand out in certain regions. If there's a lot of crashes and a lot of crop damage in one region, they're probably going to hand out a lot of extra tags in that region. If there's lower numbers in a different region, that region will get fewer tags. So they try to kind of maintain what they view as a safe and stable population. Okay, and then we've already talked about this a little bit, right? Overshooting carrying capacity. So over time, the population size will grow. It'll potentially surpass that carrying capacity, but then you're gonna have it's not gonna last very long, and you're gonna have this die off because that environment can't sustain the overshoot for very long. And then this undershoot usually will only last for a little while, and then it'll kind of come back. And it really depends on what's driving that overshoot or driving that undershoot, right? You can have very severe crashes if disease breaks out, or you can have very minor crashes in populations if it's just they're eating themselves out of house and home kind of thing. Those usually aren't as severe. But maybe other things like if there's a forest fire that burns a forest and burns a bunch of fields, and we're talking about deer again, or rabbits or mice that depend on the vegetation, that might be really detrimental to them that they don't have that food resource due to some type of natural disaster even. And then here's the visual of the wolf and the moose, where the wolf is lagging behind the moose that we saw, right? Where we have the moose in green, we have an increase in population and an increase in wolves. And then we have this drop off here, and then we're going to have a followed by a sharp drop off in the wolves. An increase is going to allow the wolves to recover, but then that's going to cause the moose to decrease, which then will later cause the wolves to decrease. It's not instantaneous. There's that lag effect. Okay, and then this just talks about population cycles. Again, over time they've measured, this was kind of human induced because they were breeding these falcons and exporting them, and falconry was really popular in the 1700s. So they'd have a really big boom population, they'd capture a lot of them, they'd export a lot, then the sales would go down, and they had these high fluctuations in populations because there was a demand for these falcons. And then later in the late 1700s, 1800s, falconry kind of dropped off. So they let the population drop off to more natural levels because they weren't exporting as many. This example here with the grouse, it shows that there's three different kind of species of grouse in two different locations. So all three overlapped in these two different locations, and they all kind of mirrored the same population fluctuations over time. And the point of this is that there can be some very large scale effects that you're not going to necessarily just see, isolated over here, but rather maybe the climate effects are driving the population cycles over this larger area. It can affect multiple populations or regions at the same time. And this just talks about a little bit more about the lag behind the growth. So you'll see more regular population fluctuations over time if there's a lag effect. And some of that lag effect, the example we had with the wolves was it takes time for them to build up those resources and reproduce. They're not going to eat a bunch of moose in one day and then have, offspring the next day. It takes months to years for that population potentially to grow and actually have a negative effect on those moose, where they actually continue to grow and keep feeding themselves and keep knocking down that moose. So it's the lag effect essentially showing that it's not an instantaneous cycle. Okay, so this is talking about modeling delayed density dependence. And this goes, I think, a little beyond our level that we need to. We'll need to understand this modeling concept conceptually, but we're not going to have to do any calculating for density dependence. It's more important to kind of understand what these different patterns are showing, right? So conceptually, we have a population growing, hitting its carrying capacity, and stabilizing. So this is a very stable population, right? This population has kind of a dampening oscillation where it overshoots and then gets pushed down to undershoot, and then it overshoots again, not quite as severe, and then it's slowly going to be, more stabilizing. So maybe there was something here like really heavy rains in the spring that made resources really abundant, so they overshot it, and then those rains kind of stopped, and the resources started going back to more normal net levels or stable levels. So that's why they're starting maybe to stabilize a little bit over time. And then this population is going through repeated changes, right? So we call this the stable limit cycle, right? Where these peaks are the same size. And this is because there's probably something happening in the population. This could be a predator-prey effect potentially. This could be some other type of disturbance that's driving the regular overshoot and the regular undershoot. Or these animals might be reproducing really quickly. And then those cases, the lag is less severe. So you're going to see more increased oscillations. And these are going to be more stable above and below the carrying capacity.
So it's called stable because the oscillations are equal each time?
Yeah, stable limit cycle because the cycling is essentially stable. These peaks are equal. And this is called dampening because the effect is dampened, right? Where it overshoots, then it overshoots less, and if it keeps going, it'll eventually kind of stabilize. My computer not charging. Oh no. Okay, sorry. I didn't plug my plug-in all the way. That was close. But we're good. We're charging now. All right, moving forward. We survived the outlet capacitor. Okay, and then this one was kind of neat, showing that there's other factors that can affect the oscillation. So the individuals themselves. So this species right here can actually kind of conserve energy and even pass it on to the next generation. So it's going to potentially have, it can last longer. So, if it's running out of energy, but it has reserves, it can continue to produce and continue to grow. But then you're going to see a pretty severe crash when it runs out of resources at a higher level versus this one can't reserve or preserve energy or pass it on, right? So you're going to have growth and you're going to have a little bit of an overshoot and then a drop off, and then it's going to have more, maybe those dampening oscillations. And the effect is going to be, it's going to stabilize a little quicker, where, it might seem advantageous to be able to preserve energy, but if it does it for too long, it can actually maybe be disadvantageous and it crashes very severely, almost to nothing, and then has to regrow itself. But it's more kind of life history, different species and how we can have different results from what we might predict based on what they do. And this experiment was kind of interesting because it had two groups. It had one group where there was unlimited food for adults, but the larval stage did have a limited amount of food. So what the adults would do is they would eat and have tons of resources, continuously lay a bunch of eggs, and then those eggs would hatch, turn into larvae, and they would keep laying eggs, but the larvae would eat themselves out of resource and they would not develop correctly. They wouldn't be able to metamorphosize because they didn't reach their energy threshold. And then you would have these crashes to where some larvae would be able to survive once the numbers crash. And then you would have, there's a bunch of adults again. The adults would keep eating. So you keep getting these crashes because the adults feel they have unlimited resources, so they reproduce at really high levels, but the larvae have limited resources, and the larval stage is what's crashing. And then what happened in the second group is they had unlimited food for adults, so they saw the same pattern as above, but halfway through the experiment, they switched it to they limited the food for the adults. So the adults increased their numbers, but they weren't producing, an overabundance of eggs anymore when they had limited food. So the larvae weren't in as high levels of competition, and they were able to produce adults more regularly. So that's why they didn't have these crashes anymore. And it kind of better stabilized the environment or the population rather, even though all life stages now had limited food. So limited food here was kind of good because it didn't essentially make the adults think that they could reproduce unlimited. So okay. Then this is talking about a little bit about delayed density dependence in flaxweed. And it uses the logistic growth model, even though it talks about, where is it? The delayed density dependence model. They give us a carrying capacity, they give us a growth rate, and they give us this tau value of 1. And then they give us this where we're supposed to include tau in the model. But as you see in the example, I don't know exactly why they just did the logistic growth for it. It works. You're not going to get tested on delayed density dependence using this model. You are potentially going to get tested on logistic growth. So this is some free extra practice that's a little misplaced, but it works for us actually in the long run. Right? We have our equation, we have the numbers that it gave us. We plug in our growth rate, our initial population, our population at year 1, and our carrying capacity, and we can estimate in the next year that the population is going to be 20 added to the population. And we take that 20 and then we plug it in again. Right now we have N2, so the population of 2, the 20 we calculated gets plugged in here. Oh, I can't highlight it, shoot. We still have the same R value. N3 we know is going to be 40. So we can plug that in and it gives us 35 for that particular year. And then we're going to add the 2 years together. So this is where we have 35 and 40 from the previous year to give us our value of 75. And if we go to the feedback on critical thinking, it gives you multiple steps on how they calculated it. And they also then give you the table that they filled in here. And I'll slide my notes over here so you can see it where I calculated it. I can't say those two words together. Year 1, we were given 10 plants. Year 2, we were given 20 plants. And then we calculate year 3, year 4, and year 5. And we change these values in the equation, right? To calculate year 3, we need the value from year 2 and 1. We plug those values in that we were given up here. The R we were also given in the question. It gives us our 19.8, which we can round to 20 if we want. And we add that to the previous year to give us 39.8. So 19 plus 20 gives us 39.8 or 40, depending on how we want to round it up. And then for year 4, we switch these values to N3 and N2. And we calculated our N3 right here. We have our N2 up here. So that's where the 39 and the 20 come from. And gives us 35 for year 4. And then we can add that to year 3 to give us the total value of 74.8. And then for year 5, we change these values now to N4 and N3. So just building on it will give us our values, and we just already need to add them together. And that's for these, where we had 10, 20, 39, 74, 124, and so on. So was there a question?
Other than understanding the concept, I wonder how much time I should spend on the equation.
I would say it would be worth knowing how to calculate, up to 5 years. I'm not going to have you calculate an entire, 15-year data set and make a figure for it. That would be nice, but you might be able to need to calculate from year to year. And if you went ahead and you carried out that calculation, you see that some years the change in population is positive, some years it's negative, and we kind of see this, slight dampening oscillation because the peaks are going down a little bit each year. Okay, so this is talking about random events can cause populations to become extinct. What are some of the random events that they talked about?
Natural disasters.
Yeah, right. So if you have a small island or a small area and therefore, kind of a smaller population, if you have a natural disaster such as a flood, a fire, a volcanic eruption, that can cause, extinctions in certain areas. And the smaller the population, the higher the probability of that population going extinct. And that's really what this figure shows here. We can read this usually. What we have, it doesn't have the label, but it has population on the x-axis here, and it has probability of extinction. So we have low population at 0 or close to 0. The data point is, it's going to have a higher probability. There's less individuals, right? For a fire to kill 10 individuals is more common than for a fire to kill 10,000 individuals. And so it just shows that negative trend, the probability gets lowered as we increase the population size. And then it talks a little bit about a couple different models, right? A stochastic model versus a deterministic model. And a deterministic model, that's designed to predict a result without accounting for random variation. So it assumes a single birth rate and death rate for each individual in the population. The stochastic model, on the other hand, that incorporates some random variation in population growth rates. And as far as understanding them, being able to tell them apart or define each of them is about as deep as we need to go for those types of models. We're not going to have to do any math or any drawings for this type of model. They don't really get into that detail. And this kind of just shows probability of extinction again based on population size and time to that extinction event, right? So a smaller population is going to have relatively high probability of extinction, and it's going to reach that potential extinction faster than would a larger population. Okay, are there any other additional questions from this module in Cogbooks? And again, you can always, shoot me an email or a message later, or anybody watching this that isn't able to join us, I can send me a message with questions as well. Okay, let's move on to the third module. This one talks about age structure population. And I will say these figures and understanding them conceptually is going to be important for the exam. You're going to see them again. What are they telling us, right? So we have population on the x-axis, and it's kind of it's a split axis, right? So 0's in the middle, blue is male, red is female, so it just divides it by sex. And if we go left from the middle, the population increases. If we go right from the middle, the population of females increases. So increase in male, increase in female. And then on the y-axis, we have age, and we have older populations at the top, and they get younger as we go down the y-axis, right? So that's kind of how we look at reading these figures. So what is this pattern where it's getting wider at the base telling us? Like, how are we going to describe what's happening with this population in India from 2017? As far as the population.
That it's going to grow or
I
increase.
would agree. This is evidence for a growing population. What is that evidence? How would we describe the evidence?
The towards the bottom where you have more, like as you go down, you have larger increases in the younger population. So as time goes on, that younger population will move up, if that makes sense.
I think you're definitely on track. Yeah, right. So we have more an older population up here, right? And as we get into the younger population, there's more and there's more, right? There's more younger, more younger. It's getting wider on both sides, right? So we're getting this like widening base, which means that the youngest population has the widest base. So this population is regularly reproducing, right? They're adding more and more people to their population. What about this population here? How would we describe its growth? Because one thing to note too is all of these people, so all of these age categories, these are all alive at the same time, right? So we have a small number of people in these age brackets, more in these age brackets, and the most in these age brackets, but they're all alive at the same time. Okay, so let's go to Germany, 2017. What is this pattern telling us? It's really narrow at the older age, which makes sense. They're all kind of, there's lower life expectancy at that age bracket. And then there seems to be more and more to about the mid 50s, and then it gets narrow again. So it is a different pattern. What does it tell us about the population?
Decreasing.
Yeah.
Yeah, it's decreasing, right? Because there was growth up to this kind of age bracket, and then this age is not replacing itself, where it's getting narrower and narrower. So maybe people on average are having less than 2 kids, per individual, less than one child. Therefore, the population is decreasing, right? Because you have it kind of wide in the middle and then narrow at the base. What about this population here? It's narrow, it gets wide, and then it kind of almost stabilizes a little bit. So what do we say about this population in the US in 2017?
Stabilizing.
Yeah, so if it's pretty stable on the edges, we're going to have a pretty stable population over time. It's not growing and it's not decreasing. So these are 3 patterns that we should, be able to recognize if we see them and describe what the population growth is in these 3 different populations. Whether it's growing, shrinking, or staying stable. Okay, so then it talks about some survivorship curves that are going to be different based on the type of species that you are. If you're a type 1, a type 2, or a type 3. So let's start at the top. Well, actually, let's talk about the axes first, right? So we have age on the x-axis that goes from 0, so young newborns, to older ages. So age is increasing from left to right. And then survivors on a log scale on the y-axis, so low survivors on the bottom and more survivor as we go to the top. All right, when it talks about a type 1 survivorship curve, what is the survivorship in the beginning? Is it high or low for young animals?
Hi.
Yeah, it's high, right? We can see it stays towards the top for quite a while. There's a slight decline, which we expect, that's happened. And then there's a sharp decline as they get older. There's a massive die-off. So these animals tend to survive, birth, have high survival rates when they're young, make it to mature stages, and then die, presumably of natural causes at a high rate when they get old. Not too surprising for too hard to describe type 1. Type 2, little different. So they all start, at the top here, but then this has a pretty linear survivorship, right? So you could say that the young don't really have a worse or a better survival probability than older organisms, right? The probability of survival stays steady pretty much through the entire life of a type 2 organism, where the probability of survival is really high early on for type 1 and then really low for when they get older. And then type 3 is the opposite, right? So we have things like, I think these are dandelions, right? So what we might see is a field has a massive amount of dandelion seeds, a bunch of them sprout out, and then they kind of choke each other out. So early on, their die off is really fast, right? So a lot of them die, the population thins out, but then there's a small amount that do survive, and that small amount that survives tends to make it to a larger or a later life stage. So that's why they have a high die off initially, and then a low level of die off if they make it uh, to later stages in their life. Are there any questions about the different survivorship or the different survivorship type curves? Okay. All right. Now the fun part, the life tables. They tell us a lot, but they take a little bit of work because there's going to be some math with these life tables for sure. So up to this point, our assumptions have been that survival and reproduction are equal for all individuals in the exponential growth model, the geometric growth model, and the logistic growth model. When we get to life tables, we see that it breaks it down by age category, right? So we have age bins, right? 0, 1, 2, 3, 4. Usually these are by year, but it doesn't have to be. It will be consistent. Like if these are months, it'll be 1 month, 2 month, 3 month. If they're years, the intervals will be the same. Then usually we have different numbers of individuals by age, right? So these are considered, 0 is considered our newborns. They're not a year old yet. The actual numbers aren't super important. It's just how we use them to do our calculations. And then we have our survival rate, which differs, right? So individuals that survive from age 0 to 1 have a 50% survival rate versus individuals that survive from age 1 to age 2 have an 80%. And the same, 50% again surviving from 2 to 3. And then there's a 0% chance that they survive from 3 to 4, which is why we have no 4-year-olds. They just don't live that long in whatever species this is. In fecundity, this is a value of their reproductive output. So not surprisingly, newborns have a fecundity value of 0, right? Most species, newborns aren't going to be reproducing. 1-year-olds have the lowest value. So they got a value of 1, which again isn't too surprising if we think about the ecology. They're still pretty young. So these are going to be, if there's any competition or sexual selection, these are going to be males that are selected usually against, aren't very competitive. So they're not going to win over, females as much or be able to establish breeding territories. So there might be some success in reproduction, but it's going to be pretty low. And then for this species, age 2, they hit their peak. They have their highest reproduction. These are probably the most fit males or the most fecund females. And then age 3, they're still able to reproduce, at a higher level than the 1-year-olds, but not quite as high as the 2-year-olds. So the reproduction drops off a little bit as they get to their final life stage. And then obviously 4-year-olds don't exist, so they're not reproducing. Okay. And then this table kind of breaks down a little bit on how we get some of these numbers. So to get the number surviving to the next class, like we talked about, that's just going to be the number of individuals at that class. So 20 individuals at age 0, their survival rate is 0.5, and that's going to be 10 that survive from 0 to 1. So this category here is the survivors from year 1 to year 2, or year 0 to year 1, however you want to kind of call it. And then fecundity are going to be those reproducing, right? So that's B of X. Those are our values. And if we want to know the number of offspring produced, we're going to have to multiply N of X by S of X by B of X, right? And we have those values up here. So we get our number of offspring produced. So we have a whole, and then we add them together. And that's 74 new offspring for this population the next year, right? So then over here, what we have is we have our census of our population 1 year later. This is our census of the population to begin with. So we have 100 individuals to start with. We have some die off because, right, they're not all going to survive. None of them are equal to 1. But we also have fecundity values. So there's, newborns. So the next year census, we have 74 total new newborns. The previous newborns of that 20, 10 of them survived to be 1-year-olds. from the previous 1-year-olds where we had 10, 8 of them survived to be 2-year-olds. The 42-year-olds, they survived at a 50% rate, so 20% of them survived. And then the 3-year-olds had a 0% survival, so all 30 of the 3-year-olds died, and that's why this value here is 0. But we had higher births than deaths, so our population for the second year is 112. So the population grew from 100 to 112 from year 1 to year 2. And then this is showing, the tables kind of again, they go through the calculations in the text here. And then if we want, we can use the geometric growth rate derivative to calculate a value of lambda, which tells us if it's greater than 1. We don't have to know on this. We won't have to calculate this, but it might give you this value on the exam. And if we know that it's above 1, it means it's more than reproducing itself. So this population would be growing, right? If it was, say, 0.8, it's under 1, we know the population is declining. If it's exactly 1, we know the population is stable. They are reproducing, but they're not more than replacing themselves. So it's keeping the population the same. We would have seen it be 100 and 100 again. And this is kind of the example where they did an 8-year project and they show you how the population is growing over time, right? And if it goes from 100 to 112 to 118, it's continually increasing. It's not surprising that the lambda values are all positive as well, right? Because that means that the population is growing. Okay, and then this is going to show how we have another variable that we can add in. So we had talked about survival rate, talked about fecundity, the number of individuals, and age, but now it has survivorship. The survivorship is going to be worded a little different, right? That's survivorship from birth to a certain age. So from 0 to 1, from 0 to 2, from 0 to 3, from 0 to 4. And Cogbooks, unfortunately, is a little loose in their writing. They don't always write survival rate when they mean S of X, or survivorship when they write L of X. And I'll show you examples of it in Cogbooks when we go over the activities. For the exam, it will be explicit that S of X is survival rate and L of X is survivorship. So I made sure of that. And then this equation up here, L2 equals L1 S1, is going to be important for being able to calculate certain values of the life table. Because what you might see is you might get a life table that's completely full, like in some of the activities, and it asks questions about the life table. You might get a life table that is not completely full, and we'll have examples of this coming up, but you're going to have to figure out, if it's asking for survivorship right here, right? It's missing the L of X column. We're going to have to add that, and then we can use this equation to actually derive the values from L of X. Because we have, we'll have L1 and we'll have S1, and we'll get into that with an actual example. I don't want to explain too much verbally before we get into that. So just, this is where they introduce this equation, all the different terms, what they mean. And then when we get into the life table activities and some practice problems at the end, I'll explain how to get the missing values, because that's going to be what you're going to see on the exam. Okay, so then briefly it introduces cohort tables versus static life tables. What is a cohort table roughly? Like, how would we describe that, and what kind of organisms would we use it for?
Cohort tables are essentially used for They do not work well for species that are highly mobile, so stationary, like plant stationary populations are non-highly mobile
Yeah,
populations.
I agree with that. And the example they use are these birds that are territorial, right? So they stay in a certain area. They're able to capture them. They put color bands on them with different combinations so they can tell individuals apart. These are also the name cohort means like, it's a specific group. When you were all freshmen in college, your cohort is your freshman class, right? So, and you can track your specific class and progress as you go through college. So what it's doing is it had these what is this finches. It captured one season. It captured all of the finches of that year, and it put these color bands on them, and then it tracked them for 15 years. That same group. It didn't put bands on necessarily on new ones. It didn't worry about the offspring that were reproduced. They just wanted to find the survival rate of that given cohort over a 15-year period. So, and you can see that survival rate fluctuated. And it doesn't mean that that's how many are left, right? So in the beginning, they didn't have a very high survival rate. It was like 40, a little over 40%, which isn't surprising if they're doing this with nestlings. They tend to have the lowest survival rate. Then when they got a little bit older, over the years, their survival rates were pretty high. Every year, some are dying, so the population is going down, even though the survival rate's going up. It's just meaning that the percentage of them dying from year to year is less over this period. And then for whatever reason, there was kind of a dip where kind of a die off here at mid-age. Maybe there was a couple of rough years of drought, or high predation levels, or high levels of competition, or maybe there was virus or something that came through there, or climate effects. And then the survival rate increased, so the conditions must have improved, or the birds that survived were just really good at surviving, right? We don't know exactly why, but we can just see what their survival rate over time is. And then eventually, they all die because they die of old age. So it crashes at the very end. So this is something that's good for short-lived organisms. Why would something that's long-lived, like say a Galapagos tortoise, why would this method be challenging for a researcher?
Time.
Yeah, right. The Galapagos tortoise is probably one. It's going to outlive the researcher, which is definitely going to outlive their career. So if they did this for tortoises, they would have to have, a collaboration where someone's the lead for a time being, and then they pass it on, and then they're not even going to see their work finished. So this would be, the tortoises could be over 100-year study or more. Which if people, doing science know, getting funding for a single project for that long is also very challenging. So. Okay, yeah, so that covers cohort tables. And static life tables are a little different, right? So these are more of a snapshot in time, and they incorporate all the organisms of all the different life stages. So the newborns up to their last year, and they kind of look at a snapshot of like maybe one growing season or one 15-year period potentially. So they don't track the organisms because these are more mobile organisms. So they can, but knowing what the difference is between the ages can give you a good idea of, if you have low numbers at the higher ages, you can start estimating, what is kind of their die off, what is their survival rate in the newborns compared to the 1-year-olds. So you can get kind of the same information, but for different age classes, and you don't have to track these organisms over the course of their life, or you don't have to, like, if they're really mobile, you don't have to, finding them might be really difficult. So knowing briefly kind of some of the differences between cohort life tables and static life tables, what they're used for, the types of organisms, what they tell us is going to be, important for the exam. All right, so let's get into some of the activities now. Okay, so this one I think is kind of good because it gives us verbal definitions of what we're actually doing with these equations or what we're doing with the parameters. So pretty simple, right? Just to fill it in, but I think this is nice to reference and it, like, especially telling us what survivorship versus kind of fecundity versus survival rate means. So age, right? Just we can count. So 1, 2, 3, fill it in. This N of X is the number of the population of that age class. So 0 is number of newborns. number of individuals alive at age 1, alive at age 2, 3, age 4. And this is survival from birth to age 1. This is survival from ages 2 to 3, survival from ages 3 to 4. So this is going to be a 1-year snapshot of survival. So what we're missing, obviously, is survival of ages 1 to 2. And this is survivorship to that age, right? So this is survivorship to birth, survivorship to age 1, survivorship to age 2, survivorship to age 3, and this is from birth. So this would be survivorship to age 4. And then this is our fecundity, right? And this is fecundity by age. So fecundity age 1, fecundity age 2, 3, 4, and 5, and so on. So I'm gonna spend a ton of time on it unless there's any questions, but it's a good way to verbally say, what we're doing. Okay. What did I do? Oh, I went into this. I don't know why. I went into another one, I guess. But we don't need to do it twice. Okay. So this is more similar probably to what you'll actually see in the exam. You'll be given a life table. They're going to come with a different amount of columns. These first ones are pretty simple. All the information we can derive from this life table. But I will say, at this point, you might need to add more columns to your life table. So scratch paper is going to probably be important for this exam. You might need to sum up certain columns. You might need to, multiply certain columns together to create the new column and then sum it up to get some of the variables or the values that they're asking for. This first one, so which value equals survivorship from birth to 4 years of age? So if we're saying survivorship from birth to a certain age, what variable are we talking about?
SX.
That would be survival rate from one age category to the next immediate age category. So from like 0 to 1, 1 to 2, 2 to 3, survivorship is going to be L of X. Right? And if we're going from birth to 4 years of age, we want to find 4 years of age, L of X, that's where we get the 0.5 from. And this one asks which value equals the fecundity at age 4? And which column is fecundity again?
B of X.
Yeah, B of X, right? So we know it's in this column, asking at age 4, fecundity is going to be 1, right? So which value equals the number of individuals alive at age 1, right? So that's going to be our N of X, age 1, individuals alive, 500, right? That's where that value comes from. Okay, and this says which value equals survivorship from age 0 to age 1 of years. And this is where I don't like cogbooks because it shouldn't say survivorship, it should say survival rate, because that's how they defined it initially. And this is where they get a little loose with it. So if we say survival rate from age of 0 years to age of 1 years, that leaves us with what we said was survival rate, S of X, right? So that's the first value from 0 to 1, that's the survival rate. Okay. All right. Now this one, same idea, right? It gives us another life table. We've got age categories, all our NX values, all our survival rate, SX values, all our survivorship, SLX values, and all our fecundity values, BX. Right? So we just practice again, right? Which value equals the number of individuals alive at age 5? So we know age 5, number of individuals alive, that's going to be our population. So that's where we get our 548 from. Which value equals survivorship from birth to 3 years of age? Survivorship is our LX. And if it's from birth to age 3, we have LX, age 3, and that gives us our 0.917.
Would you please describe the difference between SX and LX?
SX is defined as survival rate, and that tells us from 1 year to the next. So that's going to tell us how newborns, of the 1,000 of them, 94% of them are going to survive to be 1-year-olds the following year.
And LX?
And that's our survivorship. And that's the number of female offspring per reproductive female. So that's considering the females essentially that survive. It's female survival. This is overall survival. And that's why usually these values are larger or smaller than these values.
Only female.
Yes. The number of female offspring per reproductive female. And this is pooling males and females, so everybody in that age category. Okay. And then number 3 is asking us which value equals the fecundity at age 1, right? So fecundity is our B of X column, age 1. That value is 0, right? So newborns, they don't reproduce. 1-year-olds, they don't reproduce. 2-year-olds, they don't reproduce. Reproduction doesn't occur until age 3. Okay. And number 4, that's asking us which value equals the survivorship from the age of 2 years to the age of 3 years. And again, I don't like how this should say survival rate because that's doing from years 2 to 3. So this is, I think, another error in Cockbook. So if we replace it with survival rate from ages 2 to 3 years, we go up to our S of X category. We can get our 0.984 value, right? Because its age is, 2 to 3 years. So 2 to 3, it's going to be 2-year-olds surviving to 3-year-olds. The 2-year-olds are going to survive at a 98.4% survival rate. Okay, so then this says, use the life table below to answer the following questions. Which value equals the net reproductive rate, rho? How do we figure this out?
Add up LX and the LXBX column.
Yeah, exactly, right? So we know the value of rho, r sub 0, equals the sum of LX, BLX, right? And they give us that column, LX, BX, all the individual values, but they don't give us the sum. So this is where we need to use the information in the table to calculate a value. So we do 0 plus 0 plus 0.5 plus 0.45 plus 0.05, and that equals 1. So we have the information we need, but we got to do a little bit of math to get a missing value. Okay, and then this life table, there is a problem with this activity. It's doable. It's asking us to find missing values of either BX, LX, or LXBX. And we know that one way to do that is if we take LXBX equals, if we multiply these two together, we get this, right? So 1 times 0 is 0. 0.94 times 0 is 0. Then we have 0.81 times something equals 0.13. And what we need to do then, so it's like this times x equals that. So we divide from this side. So we do 0.13 divided by 0.8, and that's going to get us 0.16. The problem with this page is if we want to use that L2 equals S1 L1 equation, the values that they don't work. So whoever put this together had the intention of using the LXBX equals this LXBX, but forgot to put in appropriate values with the S. And so if we ignore that part of the table, it does work for the LXBX equation, but some people pointed out that you should be able to do it two ways, which is correct, but the tables with the SX values don't always work out. Does that make sense?
Not to spend a lot of time on this one, huh?
No, I would say, well, just know going into it, just focus on the last three columns. Like that way it'll work out real easy. The math actually plays out. So what it looks like, here, I'll show my notes on it. You're going to have this LXBX equals LX times BX, and we're given three or two out of the three values, right? We're usually given 0.13 and 0.81 for the first one, and then in order to solve for this BX, we have to move it over, or we have to move the 0.8 over. So the 0.13 is divided by the 0.18, and then we solve it all by shifting one of the values or multiplying them together. Does that make sense how to use these three on the right for the group?
Yeah.
Okay. Okay, so that's as far as I think we need to go in the actual module, but I do want to do a few practice problems with you to show you an example. You might see something very similar on the exam. So you might get something that looks like this, where it's an incomplete life table, right? And the question is, what is the survivorship of an individual from birth to the age of 3 years? So we have age, 0 through 3. So we know it goes far enough. We have S of X, which is survival rate. We have B of X, which is fecundity. But aren't we missing survivorship, L of X, right? So you need to recognize we're missing that, and you're going to have to add a new column, L of X. Having L of X and S of X, and this kind of will clear up the air a little bit on the previous page. How do we get L of X? How do we get these values? What's one thing that we know about the L of X1 that's always consistent?
That it's 0?
Not 0, because this is survivorship, right? So this is if they're born, we know that they're alive, right? This doesn't include stillborns and death, right? So this includes the initial births that are alive. So we know that L of X, the first value is always going to be 1 because it's 100%. They're always alive in this category. So that's kind of one thing that's important to remember. Now we have all of our S of X values, and we have our first LX value. We have LX1. How do we get LX2?
Is that the L1, S1 multiplying it?
Yeah, we use this equation, right? L2 equals S1 times L1. and we have S1 0.6, and we have L1 1. So now we have L2 1 times 0.6 is 0.6, right? So we just multiplied these two values together to get this value. And we can do the same thing for all of the values, right? We have this value. So now to get this, we do L3 is what we want. That's S2, what we have, times L2, which we just calculated. So 0.5 times 0.6 is 0.3. And to get L4, we do the same thing, right? We have S3 already. We just calculated L3. We multiply those two together, 0.9 times 0.3, and we get 0.27. So the survivorship of an individual from birth to 3 years of age is 0.27. So that's how we would solve this problem. But you're probably going to see questions, this could be a short answer question that's math-based, right? The first part, A, solve the survivorship of the individual. We did it. The second part, what is the net reproductive rate? We just talked about that, right? It's rho, R sub 0, equals the sum of LX BX. So we don't have the LX BX column, but we have the individual BXs and the individual LXs, right? We just filled that in. So we need to add a new column of LX BX, right? So then we can use our data we have. 0 times 1 is 0. 1 times 0.85 is 0.85. 3 times 0.48 is 1.3. 2 times 0.46 is 0.39. And then we know it's the summation of this. So the net reproductive rate is 3.9. Right? Okay, so that's part B. We solved for rho. Now part C. Do we expect this population to increase or decrease, and why? What are we going to base this answer on?
Whether it's over or under 1.
Yeah, right. So we're going to base it on our value of rho, our net reproductive rate. So we have a 3, that's over 1. So is it going to grow or is it going to decrease?
Increase.
Yeah, right. We're going to say we expect it to increase because the value of rho is 3, which means this female is more than replacing herself with more females. So that's why it's going to grow. So that is this, practice on a multi-part math problem. Let's try one more. So say you get this life table. We get age, we get our LX column, right? Our survival. And we get B of X, which is our fecundity. So we get our survivorship, to get it correct, for L of X. And then B of X is our fecundity. And then we get LX BX. And it asks us which value equals the annual survival rate of 4-year-olds. So what column are we missing?
S of X.
Yeah, right. So we're missing S of X. So we're going to have to add that column. I would do this on scratch paper myself personally. And then we have to go to 4-year-olds at least. So we know that we need to fill in S of X. How do we go about doing that based on the data that we have? Unfortunately, we don't know the first value of S of X. It's not always 1 like L of X. So we notice L of X is 1 over here, but we do know some equations. What values do we have that will help us get the S of X values that we want? What about the equation that we just used, right? It uses 2 values of L and 1 value of S of X. We have all our values of L of X, so we should be able to use L1 and L2 to solve for S1. What that looks like, right? So if we have L2 and we have L1, we just need to find, it'll help us figure out what S1 is. We take L2 and we divide it by L1. So we get 0.6 divided by 1, and that gives us 0.6. Pretty straightforward. And then we have L3 and L2. We have L4 and L3, L5 and L4, L6 and L5. We're just missing all our S's. We plug those all in, do our division, right? So here we have, to get S2, we need to have L3 divided by L2. So that's the 0.56 divided by 0.6, and that gets us 0.93. And we can do it for all of the S values. And actually, we can even do it for 5, but what we're asking for is up to 4. So the answer is which value equals the annual survival rate of 4-year-olds? And that would be 4-year-olds, S of X is 0.5, right? Is this making sense?
Somewhat.
Okay, so this might be something to review a little bit, but it's, this is the equation that we're using. We have L2 and L1, and it says basically you have 2 out of the 3 variables, and you need to solve for the missing variable. And we can do that repeatedly by using the equation with the different values that we are given in L of X to fill in our S of X values.
Okay, so we're specifically just using L of X, the one below it, dividing the one below it, or dividing the one below by the one above, just LX to get all the SXs.
Yeah, because
of X's.
yes, because it's really an algebra problem, right? Where we have this value and we don't have this value and we have this value, so we're solving for S of 1 or we're solving for X, right? Like in algebra. And if you have X times a value, you take the value over to this side to isolate X or S of 1, and then it turns into just a simple division problem each time, right? Because to get S of 1, we have to isolate it by itself by moving L1 to the left side of the equal sign, and that goes underneath the L2. So it's L2 divided by L1, and then it's L3 divided by L2, L4 divided by L3, and so on, using that equation to get our missing S values.
Okay, that makes sense. Thanks.
And I didn't extend this one, but if it asked you for the value of rho, the net reproductive rate, how would we get that?
Add up all the LX, BX would be the.
Yeah, right. We would just take the summation or add all of these together. And that would give us a value of 1.99. And we could say, is the population growing or shrinking? Why? So based on 199, what would we say?
It's growing.
Yeah, because it's above 1. So the female is more than replacing herself in the population. So the population should be growing.
Now, if BX is missing and we need to find BX, do we do it in the same fashion? Like, is there going to be an example where fecundity is missing?
No, there won't be an example where fecundity is missing because there's not an equation that we can use with this information to derive it. So
Okay.
really, it's going to be the LX and SX kind of equations. But you might get questions from the BX column, like what is the fecundity of 3-year-olds? Or, where does reproduction begin? At what age in this population? What is the lifespan kind of this population or the longevity of this population?
What do you mean by that? the lifespan. Can you elaborate?
So like, how on average, well, not even on average, what is the oldest age this population can reach based on this life table?
5.
Yeah, it would be age 5, right? Because 5 has some survivorship and some survivorship, but the survival rate of 5-year-olds to 6-year-olds is 0. So there's no 6-year-olds. So the oldest an individual can be is 5. Does that answer your question?
Yes, thanks.
Okay, good. No problem. Yeah, I will be honest, this exam tends to be the most challenging of the 5 exams because it is math heavy, but with practice and reviewing this, I think it can be done. So
I haven't, but where do we reach your video? I'm going to have to review this.
sure, I can fill that to this group. So if we stop, well, we can shrink this down. We go, where is it? All right, so if we go to the home page on Canvas, you would go then to the modules tab. And then if we scroll down to module 0, we have virtual office hours link. We click on that. This is where I post all the links to the videos, and I'll
Thank you.
post the other one tonight. Yeah,
Thank
no
you.
problem. It's a good question. Okay, are there any other questions from the 3rd module?
Is there any way that you would be willing to share like your problems we went over tonight?
I mean, they'll be on the video, so you can pull everything from there.
Okay,
Does that work?
sure.
Okay.
I do have a question about the notes, real quick.
Sure.
Does it have to be handwritten or can it be typed?
Yeah, so that's the only stipulation on them is they have to be handwritten.
Okay, thanks.
But they can be absolutely anything you want to put. They can be definitions, they can be practice problems, they can be the equations with notes about what they mean. They can be your notes that you've taken from the reading. And the only other stipulation is you have to show it to the computer screen. So just a couple of seconds front and back because you can use both sides just so we can see what's on there real quick. Okay. If there's no more questions, we can go ahead and call it a session. I think we covered a lot tonight. Just go over the practice problems in the video and go over the activities again. And just always not only be able to get the answer, but explain a little bit of how you got the answer or why the answer is what it is. That's going to help you conceptually answer some questions on the exam too. But I want to thank everybody here for joining and participating. And
Thank you.
I will see you guys in the next office hour.
Thank you.
Thanks.
Have a good night.